permit me There is a peculiar beauty in watching something utterly unpredictable submit itself to mathematics. At first glance, Brownian motion appears to mock the ambitions of theoretical physics. How does one calculate a zigzag? How does one predict a tremor that has no memory of its previous step? The path of a Brownian particle is so irregular that in the strict mathematical sense it possesses no well-defined velocity. If you attempt to measure its speed by dividing displacement by an ever smaller interval of time, the value does not converge, it diverges. The motion becomes more violent the closer you look, and yet within this wildness a subtle regularity hides. The essential move is philosophical as much as mathematical. Abandon the attempt to describe a single trajectory. Instead, describe the statistics of many trajectories. We trade certainty for probability, precision for expectation. Values, what we lose in determinism, we regain in universality. The cornerstone of this quantitative description is the relation between displacement and time. In narration, we state it as follows. The mean square displacement of a particle along one dimension equals 2 times the diffusion coefficient multiplied by time. Written symbolically, one expresses this as angle bracket x squared angle bracket equals to dt. This relation is deceptively simple. It tells us that the average of the square of the displacement grows linearly with time, not quadratically as it would for uniform acceleration, not remaining constant as it would for confinement, but linearly. The particle spreads steadily, like ink diffusing in water, in 3 dimensions. The generalization follows naturally. In narration, one says that the mean square displacement in space equals 6 times the diffusion coefficient multiplied by time. Symbolically, this appears as angle bracket r squared angle bracket equals 6 dt. Already we see something extraordinary. Time governs the growth of uncertainty. The longer we wait, the broader the spread. The randomness accumulates, but what is this diffusion coefficient d? It is not an arbitrary parameter. It encodes the microscopic physics from thermodynamic reasoning and hydrodynamics. One finds that the diffusion coefficient equals Boltzmann's constant multiplied by temperature, divided by 6 pi times the viscosity of the fluid multiplied by the radius of the particle. In narration, we express it as d equals k sub b times t divided by 6 pi etar. Observe the drama contained in this single expression, Boltzmann's constant. That quiet bridge between microscopic energy and macroscopic temperature appears. Temperature, representing molecular agitation, pushes the particle more vigorously as it increases. Viscosity, the internal friction of the fluid, resists motion. The radius of the particle determines how strongly it feels this resistance. Each quantity plays a role, like characters in a carefully balanced play. Now combine these results. Substitute the expression for d into the mean square displacement formula. In narration, we find that the mean square displacement equals 2 times Boltzmann's constant times temperature divided by 6 pi times viscosity times radius, all multiplied by time. Even without symbolic shorthand, the meaning is luminous. By measuring how far particles wander over time, and knowing the temperature, viscosity, and size of the particles, we can determine Boltzmann's constant. And once Boltzmann's constant is known, Avogadro's number follows, because Boltzmann's constant equals the universal gas constant divided by Avogadro's number. In narration, this reads, K sub b equals R divided by N sub A. Thus, through the jitter of microscopic particles, we gain access to one of the most fundamental constants of nature, the number of molecules in a mole of substance. This is not abstraction, this is measurement through fluctuation, but there is still more subtlety. The probability distribution of particle positions satisfies a differential equation known as the diffusion equation. In narration, it states that the partial derivative of the probability density with respect to time equals the diffusion coefficient multiplied by the second partial derivative of the probability density with respect to position. Symbolically, one writes partial p over partial t equals d times partial squared p over partial x squared. This equation governs how probability itself flows through space. It is as if uncertainty were a fluid, spreading according to precise mathematical laws. From it one derives the Gaussian distribution, the elegant bell curve that describes the likelihood of finding a particle at a given displacement. The irony is delicious. The most Irregular motion imaginable gives rise to one of the most symmetric mathematical forms, and here we encounter a profound lesson. Fluctuation is not noise to be ignored. It is structure to be understood. The mathematics of Brownian motion does not tame randomness, it reveals its architecture. Every unpredictable collision contributes to a predictable spread. Every microscopic impulse participates in a grand statistical symmetry. Thus, the mathematics of fluctuation teaches us humility. Nature may deny us the path of a single grain, but she grants us the law governing the multitude. In surrendering determinism, we discover a deeper constancy. In accepting randomness, we uncover order more subtle and more universal than any straight line drawn by certainty. The trembling particle becomes a mathematician, inscribing its equations not in chalk but in motion. When one reflects upon Brownian motion, one might be tempted to regard it as a charming curiosity, a botanical oddity elevated to physical explanation. But such a view would miss its true grandeur. Brownian motion did not merely confirm the existence of atoms. It reshaped the method of physics itself. It compelled us to admit that nature, at her most fundamental level, speaks the language of statistics. Before this shift, thermodynamics stood as a majestic but somewhat mysterious edifice. We knew its laws, the conservation of energy, the increase of entropy, but their microscopic origins were debated. Why must entropy increase? Why does heat flow from hot to cold? The equations of thermodynamics were precise, yet their foundation seemed almost philosophical rather than mechanical. Statistical mechanics, pioneered by Ludwig Boltzmann and James Clerk Maxwell, proposed that thermodynamic laws emerge from the collective behavior of countless molecules. Entropy, in this view, was not an abstract tendency toward disorder, but a measure of the number of microscopic configurations corresponding to a macroscopic state. In narration, Boltzmann's profound insight is written as S equals K sub B times the natural logarithm of W. Symbolically, one writes S equals K sub B lane W. Here S is entropy, K sub B is Boltzmann's constant, and W represents the number of microscopic arrangements consistent with what we observe macroscopically. This equation whispers a radical idea. The arrow of time is statistical. It is not imposed by force but by overwhelming probability. Yet for many physicists of the 19th century, this statistical interpretation seemed unsatisfactory. They preferred deterministic laws like those of Newton. They suspected that probability merely concealed ignorance. Brownian motion delivered the decisive argument. In the trembling of suspended particles, we saw probability acting not as a veil over hidden determinism, but as an essential tool. The diffusion equation expressed in narration as the partial derivative of probability with respect to time equals the diffusion coefficient multiplied by the second partial derivative of probability with respect to position demonstrated that probability itself evolves according to precise laws. Symbolically, this is written as partial p over partial t equals d times partial squared p over partial x squared. This equation does not track individual molecules. It governs the flow of likelihood. It tells us how uncertainty spreads, and its solutions, the Gaussian distributions, are not approximations, they are exact statistical predictions confirmed by experiment. Thus, physics expanded its vocabulary. It became legitimate to describe systems in terms of averages and distributions. The mean square displacement relation stated in narration as the average of the square of displacement equals 2 times the diffusion coefficient multiplied by time became a prototype for countless other statistical laws. Symbolically, angle bracket x squared angle bracket equals 2 dt. From this simple linear growth of variance with time emerged a new understanding of fluctuation and dissipation. The same molecular agitation that causes random motion also determines frictional resistance. Temperature drives motion. Viscosity restrains it. These dual roles reflect a deeper symmetry between randomness and order. Indeed, one can describe the balance between random forces and frictional drag through what later became known as the fluctuation dissipation principle. In narration, the average kinetic energy of a particle in thermal equilibrium equals 1/2 times Boltzmann's constant times temperature per degree of freedom. Symbolically, one writes 1/2 mv squared equals 1/2 k sub bt. Here we see temperature translated into microscopic motion. Heat is not mystical. It is kinetic energy distributed statistically among countless particles. Brownian motion therefore stands at the intersection of mechanics and thermodynamics. It unites them. It shows that the smooth laws governing gases and liquids arise from innumerable random impacts. Pressure becomes the average momentum transfer of molecules striking a surface. Diffusion becomes the cumulative effect of random steps. Entropy becomes the logarithm of multiplicity. But the influence did not stop there. The mathematics of Brownian motion, random walks, probability distributions, stochastic processes would later infiltrate. Quantum mechanics, the uncertainty intrinsic to quantum systems echoes the probabilistic framework pioneered in statistical physics. Even financial markets, with their unpredictable fluctuations, are modeled using equations structurally similar to the diffusion equation. Thus, a pollen grain dancing in water helped prepare humanity for the probabilistic worldview of the 20th century. There is a philosophical tenderness in this transformation. We began by seeking certainty in precise trajectories. We ended by embracing probability as fundamental. The world did not become less lawful, it became more subtle. Statistical physics teaches us that order is not imposed from above. It emerges from below. The macroscopic calm of a glass of water hides molecular turbulence. The equilibrium of a system is not stillness but balanced chaos. Brownian motion was the visible signature of this invisible symphony. Through it, we learned that nature need not guarantee predictability of the individual to ensure reliability of the collective. The trembling particle became the ambassador of a new philosophy that reality is woven not from rigid threads of determinism, but from vast tapestries of probability, and in accepting this, physics matured. It surrendered the illusion of absolute foresight and gained instead a deeper, more resilient understanding of the universe, a universe where randomness and law coexist, not as adversaries but as partners in the grand architecture of existence.